there was a question about using, well, indirectly, I guess, about how to use interlibrary loan. Where is this? About how to find papers that are hard to find. Scotty, are you from? So you had asked a question about the interlibrary, about how to find. Did you find the paper finally?
No, I didn't.
Did you try the interlibrary loan?
I did, yeah.
So you're waiting for them to come back with the request?
They didn't have it. Oh yeah, well, I guess I haven't. I searched online.
No, you have to go and say, I want this paper.
Okay.
And what they do is they have a network of libraries all the country, and some poor undergrad gets to go and scan the physical paper and then upload a PDF back to you. That's what happens.
Okay.
So if you put the request, you can guess.
So I found a book that was not in our curriculum.
Pardon me?
So I found a book that's cited in our paper that's not on ILA.
It's not ILA, okay.
No.
Well, the question is, what do you need from the book?
Well, it's like one of the main sources they use.
I know, but usually if the paper is citing a book, they're citing something very specific. If they're just citing a book in general, then you probably don't need the book. It all depends on what the citation is. But so oftentimes authors will mean, I actually mean lemma 3 on page 57, and they just cite the book because they're lazy. And the deadline is in 5 minutes.
Ours is like one of the previous solutions.
Pardon me?
This is like one of the solutions they found, and it's in the book.
If one of the previous solutions they found is in a book, then it must have been in a paper before that.
Okay.
So the question is then, is it possible to track it down? So a bit of detective work is often useful in order to see, okay, is there a different source? Maybe if it's in a book, it might be in lecture notes. If someone has in lecture notes, and again, if you read with the right keywords, if you save the keywords for what you're searching for and say lecture notes, you might actually find it. The odds are good that if it's in a book, someone's been teaching it, and then they have their notes for it. So that's another strategy you can try. And again, if you're having real trouble, just email me. I can help. I don't know if I can help, with 120 times 10 requests. But if there are a few that are really difficult to try hard, then email me. Occasionally, I'm able to find papers that others can't find. So it's an occupational skill that you might like. Okay. So. Do you have any more questions about the project report? I mean, hopefully the format is fairly self-explanatory. You just upload it as usual. It shouldn't be too hard to do. And I believe I said, I don't remember which of the two I said. Did I say you just submit as a group?
Yes.
Okay, good. So submit as a group. Okay. So, all right. So today we're going to take a change in course. I think since Halloween's coming up, it's appropriate to start with some horror, to have some horror stories. And lower bounds are in general a horror story for thinking about algorithms. And what are lower bounds? Well, all this time we've been trying to come up with ways to solve problems. Here's a problem solved. Here's a problem solve it faster. Here's a problem come with a randomized solution or a deterministic solution or a dynamic programming, whatever. Today we start on the topic of when you can't. And how to prove that you can't. Rather than just saying, well, I couldn't think of the answer. Say, no, in fact, I can't think of the answer and you can't either. And no one can. And here's why. How do you show that there are limits on what you can do for a problem? And the reason lower bounds are typically hard is because if you think about, an algorithm, right? When you want to say, I want to come up with an algorithm at a certain runtime, what you're really saying is that I have some problem. So let's call this problem P. Okay. And I have some algorithm to solve a problem. We'll call it algorithm A. So we hope or we think that algorithm A solves problem P. For now, we're not usually going to be worried about correctness, because we're going to assume we're dealing with correct algorithms. The main issue is going to be how long these algorithms take. And later on, there will be questions of, if you want it to be correct, it has to take so much time. But let's assume it's correct for now. That the main issue is how to check running time. So we have some running time for the algorithm for the problem, and what this basically means that we're saying that the running time of the algorithm for this problem is really the max over all x, the running time of the algorithm on the input of the problem, right? So we can say worst case analysis. Let's not consider randomization for now. There are other things. So this is what we call the running time of this algorithm. It's the worst case running time on any instance, and it always gives the correct answer. And so, if you want to reason about an algorithm for a problem, you have the algorithm, you do some work to analyze its running time, and this is some amount of work, and you get an answer, and then you write down the answer. It's hard, but you have a concrete object you're thinking about, the algorithm. And you look at the algorithm, you look at the steps, you count the steps, you do various things. But suppose you want to prove a lower bound. Now you could say that you want to prove a lower bound for an algorithm, but that's usually less interesting than what you really want to show. Which is you want to say, I want to prove a lower bound on any algorithm for P. In other words, I want to say that I want to prove something like, let's see, the min over all algorithms, the max over all inputs, the running time of the algorithm inputs is more than something. And this something is going to be my lower bound for P. Okay, so first of all, there's an extra level of quantifiers, right? You're not just maximizing over X, you're minimizing over A. And that minimizing over A is a lot harder. Because now I'm not just saying, let's look at any possible input. I'm saying, let's look at any possible algorithm. And an algorithm is not something where you can say, okay, I have a graph, it has, so many edges, there's a number of ways. An algorithm is, it depends on, you can come up with anything you want. We have infinite creativity. How do you even begin to reason about all possible algorithms? And that's where things get tricky. And so, you're not actually ever going to reason about all possible algorithms, because the notion just doesn't make any sense. I don't know how to do that. What you're going to reason about always is algorithms that can be implemented on a particular kind of machine. So any lower bound that I tell you, or any lower bound that anyone ever tells you, is always going to be with respect to. Particular machine. And what I mean by a machine is basically a device that has some basic atomic rules of calculation, a black box that allows you some oracle, some API, and you're only allowed to use the API. If you want to think of it, if you want the machine as a software entity, it's a black box that has calls you can make into it. If you want to think of it as a hardware entity, it has some specific operations that you can do. So when we talk about lower bounds, we are always talking about lower bounds with respect to some machine. The more powerful the machine, the higher the lower bound will be, right? Because suppose we're saying that we prove a lower bound for algorithms implemented over a counter which has, or a machine that has 1 bit of storage. That's kind of a weak machine. And if you say, well, using this machine, I really can't do sorting. You're going to say, well, yeah, you just gave me 1 bit of memory. What do you expect me to do? It's not very interesting. But if I say, no, in fact, my lower bound is over any Turing machine, it's like, okay, that's an impressive lower bound. You put it over all Turing machine. I'm willing to believe this is going to be a hard problem. It doesn't mean the problem can't be solved ever with the running time bound that I want. It just means that over these class of machines, I can't do it. And the larger the class of machines is, the more general they are, the better the lower bound is, and also the harder it is to prove it. Because now you have a lot of creativity in what you could be doing with machines. Okay? So algorithms are specific instantiations of ideas to solve particular problems. A lower bound is a way of reasoning over any algorithm over a machine to solve a particular problem. Okay. Yes?
Why didn't we use that for upper bounds? Why are we concerned about n for upper bounds?
Why are we concerned about n? Where? I'm not sure.
In terms of when we were talking about our upper bounds, we were talking about the input size of the problem, and now
Yes.
you're saying we're talking about the machine. Just trying to make the connection there. Why?
Very good. So, right. When we talk about upper bounds, we want to express our upper bound in terms of the size of the input. So we say there's some input, it has some size which we call n, and our running time of our algorithm is going to be a function of n. Right? But when we say the running time is a function of n, we don't actually mean time. What we mean is number of atomic operations in some implicit model of computation. You're right that when we talk about upper bounds, I kind of never mentioned a model of computation at all. I was implicitly using what we call the RAM model, sort of a computer. You know, if I can write it in C, that's my model that I'm working with. I also made silly assumptions like, you know, every operation is unit cost, I can access the memory in unit time, things that are obviously not true in a real architecture. So I had some implicit stylized model for a machine, and I didn't really say what it was. But you're right that in some sense I should have done that as well. I just left it, you know, ambiguous because there's sort of general consensus on what such a machine might look like. But when we're doing the lower bounds, that machine model that we would use for upper bounds is actually very hard to prove lower bounds with. It's almost impossible to say anything interesting. So we're actually going to look at very, very primitive lower bounds, very primitive machine models, and we're going to show how to prove lower bounds on that. And for the machine model that we use for upper bounds, we will prove a kind of a lower bound. In other words, we'll prove a lower bound by authority, right? I can't solve it, but neither can all these other people. There's a formal way of saying this, and we'll see how that works when we come to NP-hardness. Does that answer your question? Yeah. Okay. So I think the best way to think about this is actually to start with a simple example. So let's think about a simple example of a problem where we'd like to look at lower bounds, and we'd like to look at how to prove lower bounds. And so just a bit of notation before we start doing that. Let's try to be precise about this. So let's say we have let's see. Yeah. So what we're going to say is that a lower bound for a problem. Okay, so we're going to express this bound for. So let's say a problem P. We're going to express Tp of n, okay, as the minimum over all algorithms solving over all inputs of size n, the running time of the algorithm on the. So we're going to think of it as fixing for each value of n. What is the lower bound? What is the bound you're getting? Right. So we want to express this lower bound as a function. And so we want to put bounds on this. So we might say, for example, say something like, oh, you know, for this problem P, Tp of n is greater than or equal to, I don't know, n squared. And we might write this often as omega n squared. So people often think that, oh, omega means a lower bound, O means an upper bound. That's not quite right. It's just that when we prove lower bounds, we're proving, you know, inequalities in that direction. We're saying something is greater than or equal to something else. And so omega is a convenient way to sort of hide constants in that process. Right? They're not equivalent, but that's why. So we might say things like this. So this would be an example of a lower bound. That the running time of any algorithm over a particular class of machines for this problem on an input of size n will be n least n squared. Okay? These are the kinds of things we'd like to see. And apart from these kind of intellectual curiosity of, you know, how far can I push with my algorithm, right? Because a lower bound says, okay, I'm trying to get better and better and better and better. At some point I can stop because of the lower bound thing I can't do any better. That's one reason why we like to study lower bounds, to see how far we can push upper bounds. But there's another very important reason we like to study lower bounds for problems. And I'm wondering if anyone has any thoughts on why they might be useful, even if you're not trying to actually design an algorithm. Why might knowing that a certain problem is hard to solve be useful? Yes?
In security, we can use them as a key, as a problem that others can't solve.
So security, right? So how does this help us with security?
So I know the answer to the question, and because I know the answer, I can kind of design the question for that answer. So I kind of use that question to kind of create a kind of thing that others should try to solve, and if only if others know the answer, they can solve. Get extract information from that question.
Right.
Because solving the question is very hard, so nobody can solve
Right,
it
so-
or open the key and open the lock.
Very good. So for example, if you take, you know, factoring, which is the problem that is at the heart of many crypto systems like RSA, and not all of them, but some of them anyway. We believe, we don't know, but we believe that factoring is a hard problem, which means it is hard for any reasonable algorithm over a Turing machine to solve it in a reasonable amount of time. And so we're happy with that, because then if we base a crypto system on factoring, then for someone to, we design the crypto system very carefully so that in order for someone to break this crypto system, they would have essentially solved the factoring problem, which we believe to be hard. So there are many problems that come up in cryptography and security in general where you want a proof of hardness, not because you're trying to match an upper bound, but because you want to know this problem is in fact very hard to solve. And then you will use it in your crypto system. And then there are lots of nuances about what it means for a problem to be hard to make it sort of crypto hard as opposed to just hard to solve. And it makes things very interesting. But that's one very clear example of how knowing that a problem is hard allows you to do certain things. Another very curious thing that came up a few years ago, there was this paper that said that, so some of you may have heard about pricing of derivatives. Right? So if you're in a financial market, you construct some instrument which is saying, okay, I'm going to construct an instrument that reflects the price of wheat 10 years from now. Right? It's called a derivative because it's not based on the price of wheat right now, but it's based on some model of what you expect the price to be. And once you create a derivative, you can treat it like an actual entity, like a stock, and you can trade on it, which relies on the fact that you can price it. I have a good way of pricing something that's going to happen 10 years from now. And of course, a lot of the crashes in the stock market come from the fact that we have no idea what to do with things. But that's a different story. Right? But the whole premise of a derivatives market relies on the idea that you can price these objects carefully, that you can price them truthfully, that with sufficient information in the market, anyone can figure out the price. That's when you have a liquid market. Otherwise, if you have an asymmetric information system, your market is not fair. Then people have the information know much more, and then they can cause trouble. And it turns out a group of researchers showed that you can actually embed a computationally hard problem inside a derivative price, which means that in order to figure out the true price of this derivative, this financial instrument, you would have to solve that hard problem, which you can't do. Well, we don't think you can do, which means you can't actually price a derivative correctly, which means this whole thing is a problem. So this was a theoretical interest, but it caused a bit of kerfuffle at the time in the financial community, because basically they were trying to undermine the whole premise of using derivatives. So there's a lot of hostility to this result. But there's a whole trend, I think, ever since crypto until today, I think this idea of, rather than saying that we will try to do things that are impossible by hiding a key, for example, the way the old crypto system used to work is you hide the key in a box somewhere, don't get to it. You think now computationally, that you create objects that are provably hard to solve, or provably hard to solve efficiently, and then you use those objects to sort of embed in certain things. Okay. So I want to emphasize that this idea of a lower bound as a gadget that's helpful for building instruments is very powerful. And this comes up all the time in privacy and security and sort of other. All right. So let's look at a very simple model of computation, a very, very simple one, that we will use to try and reason about lower bounds world. So because it's a very simple model of computation, it's very limited, but it captures many algorithms that we've actually seen. So it's not completely unrealistic. Okay. And this model is called a decision tree. So a decision tree has the following basic structure. Okay. It's a tree. So you have a root node. And what we're going to do is we're going to imagine the computation as proceeding along this tree. So you have some root node. And at every node, there's going to be a question that's asked about the data at some point. Okay. I'm not going to tell you what kind of question gets asked, but some question gets asked. We might say, is the first item 5? That might be a question. Or you might say, what is the second bit of the third item 1? The only thing I want to know about these questions are the yes/no questions, which makes my life simple. You could generalize this, but it doesn't really matter. So there's a path out if the answer is yes, and there's a path out if the answer is no. And then you do some stuff. You might add, subtract, you might multiply, you might take exponents, you might take logs, you might do square roots. I don't care. I'm going to give you all that for free. Do whatever you want. Knock yourself out. But then at some point, you have another question. And maybe here you have another question. And again, this goes up. It's a tree. At the end, you reach a leaf. Okay? And the leaf is labeled. Each leaf is labeled. This will be a label 1, this is a label 0, this is a label 1. Okay? And at the end, you just report the label of the leaf. Think of it as a yes or no. this is my computational model, which means I'm only going to count. So in this computational model, I told you what you can do. Let me tell you what cost means in this model. Cost means a question. Every time I ask a question, I pay $1 for that question. So the total cost of an algorithm. So first of all, what is an algorithm in this model? An algorithm, or rather a particular run, an algorithm will be one of these trees. A particular run of the algorithm on a particular input will be some path, right? So, I might, one particular run might say, okay, based on my input, I went this way, I went this way, I went this way, I went this way, I went this way. Oh, I ended up 0, so my answer is 0. So each run of the algorithm is one path through the tree, okay? I ask a question at every step. I don't count any of the other work I do. And at the end, I reach an answer. The amount of time or the amount of cost, the amount of dollars I've spent is the number of questions I asked, which is the length of a route to leaf path. Okay? So running time. Okay? Does it make sense so far? This is how I'm charging. I'm allowed to charge an algorithm any way I want, as long as it's meaningful. Okay? So I decide to charge it this way. So notice a few things. First of all, I'm ignoring a ton of things. Is this a bad thing? Is it good? Yeah. Why am I allowed to ignore stuff? Why do you think it's okay for me to say I'm not going to charge you for any arithmetic operations you do, anything that you do that doesn't involve asking a question? Why is that okay?
Because you're getting
Sorry, wait, 1 second. Hand up, yeah. Get hand
You're
up.
saying that you want something that takes at least this time, so if you take more than this time, you're fine.
Exactly. What I'm trying to do, this is the exact opposite of what we do before. Before trying to look at our operations very carefully to make sure we never spend more time than we need. Here I'm saying, whatever. I'm trying to say it takes at least as long. You can do some other stuff. I'm going to prove a lower bound just based on the number of questions you ask. And if that lower bound is big enough, then the rest is just gravy. Of course, the lower bound may not be big enough, in which case I have a problem. Right? So that's a trade-off here. My model better be, this is what I mean, my model better be rich enough that I'm doing interesting work here. Otherwise, not interesting. So the basic idea in a lower bound is you come up with a model that's simple enough that you can reason about it, but complicated enough that it captures what you believe is really going on with your problem. In this case, I'm going to say I believe what's really going on with the problems I'm going to tell you about is the asking of questions. And that actual computation doesn't matter. For lots of other problems, this is not true. The computation matters a lot. If you're doing matrix multiplication, there are no decisions. It's just a whole bunch of calculations, in some sense, right? I mean, there may be a loop. So say, okay, I have to loop from 1 to n. But apart from that, there's no other decision being made. So in a decision tree model, matrix multiplication might look really cheap, but it's not. That's why it's not the right model for that. So now I have this model. I have a notion of time, which is the number of queries I make. And I have this notion of an algorithm, which is basically a tree. Every algorithm looks like a tree. And this is very important, right? Because I said before, it is very hard to reason about any possible algorithm. Because algorithms are variable, they involve our creativity, they can do all kinds of crazy stuff. But if I'm now saying, no, every algorithm looks like this tree, then my life is a little bit easier. Instead of reasoning about algorithms, I reason about trees. Okay, so here's a question for you. If my algorithm is a tree, and cost is the length of a route to leaf path, what would the worst case running time of an algorithm be in this language?
Infinite.
Anyone hand up someone? Yeah?
An infinite amount of time.
Why?
A recursive algorithm that keeps a loop at the top of it.
No. My algorithm is a tree. It's not recursive. There's no loops. In that case, in the language of trees, what would I express the worst case running time of an algorithm as? There was a hand up the back. Nitin? No, you had a hand up. If you didn't have a hand up, that's fine. I thought you had a hand up. Yeah, go ahead.
It's the height of the tree if you log into the base.
Wait. So there are two statements here. One is much faster than the other. So let's take the first one. It's the height of the tree. What is the height of a tree?
So all the number of levels in a tree will make the height of the tree.
So so let me draw a tree, and then tell me what the height needs to be. What is the height of this tree? Sorry?
5 including 12.
Because 1, 2, 3, 4, 5, there are 5 steps. But the height to this node is only 3 and only 1. So when you said the height of the levels, you mean the maximum height. Right? Okay, good. So the definition we have now is that the worst case running time of an algorithm in this language of trees is really the height of a tree, which is the maximum. So let's say, so this is the running time. Is equivalent to height of tree, which is equal to maximum length of root to leaf path. Right? Yes? So in previously in algorithms, we used to have a problem and we said, oh, we're going to design an algorithm, look at its running time and then count the steps. Here, we're going to say, no. My algorithm is going to be a tree. I'm going to come up with a very clever tree, and I'm going to look at the height of such a tree, the worst case height, the height of the deepest leaf. Okay. I still haven't forgotten about the next statement. I'll get to that in a second. What's a lower bound in this language? In the language of trees and heights, what do the lower bound consist of? Yes? Back at minute one.
So the lower bound across all the inputs would be the shortest way by which you can reach a input.
The shortest way for a particular tree?
Yeah.
So remember, a particular tree is a particular algorithm.
Yes.
If I'm thinking about lower bounds, I'm not allowed to think about a particular tree.
I thought you were asking lower bound across for a particular algorithm.
For a particular problem. A lower bound for a problem. Anyone?
Number of nodes in the tree. In the worst case, all the nodes are straight.
What is a particular execution of an algorithm look like in this tree? Does it walk along every single node of the tree?
Yes. No, it goes one and always.
So the number of nodes in the tree is not the point here. Yes?
Is it the minimum path over all the possible trees?
The minimum path over, but it's the, okay, so there are lots of trees. This is one tree, it's got a path of 1. Is the lower one 1?
No.
So
It's a min over a max, remember?
the maximum length.
You're looking at a lower bound would be, what is the, how do I say this? To prove a lower bound for a problem in the language of trees, what you're saying is that look at all possible trees that could solve this problem. Look at the worst case path, the longest path for each of these trees, and take the shortest of all these. Right? Because every algorithm, which is every tree, is going to have a worst case path length that's longer than that one. Does that make sense? This min-max sort of weird thing? Right? A lower bound for the problem is a minimum over, it's a lower bound, so it's a minimum over all possible algorithms. But for each algorithm, you're looking at the longest possible route to lead path. So it's a min over max. So if we want to prove a lower bound for a decision tree, we're trying to say that every single decision tree that you could come up with for this problem is going to be at least so much deeper. That's what a lower bound is. That make sense? So if every tree is at least that deep, no matter what tree you come up with, you're going to have to pay at least this much. That's your lower bound. So we've taken our goal from lower bound over all algorithms to depth of a tree, which is a much more nice and tangible notion. How do we reason about the minimum depth of any tree that could solve our problem?
But we depend on the number of minimum decisions we have to make.
Correct. It depends on many things. We still have to reason about it. And this is where we get back to your point about log n. So you said the tree has depth log n. Why? Why do you say the tree has depth log n? There's a reason for that. I mean, you're correct that a tree of a certain kind has depth log n. What kind of tree is that? Wait. Go ahead. Go ahead.
I think it's balanced tree.
Okay, so you have some idea of a tree being balanced. What in your mind, what does balanced mean?
So the height of the right and left is like
Roughly the same. So you have a picture in your mind, and you're thinking something that looks like this. Maybe it's missing one here, but basically they're balanced, right? Something like this, right? This is your idea. And you're saying for a tree like this depth is going to be something like log n, right? Okay. Under what conditions? What does n mean? Number of nodes. So the claim you're making is that a tree with n nodes will have depth log n. Of course, in one trivial sense, that's not true. In a trivial way, because it's kind of, I'm just being annoying here. But it'll have depth n. That's not the tree you were thinking of. You were thinking of a balanced tree. So there's a slightly more precise way to say what you're saying here, which is to say that, and I'll make this claim, is that any binary tree, binary meaning two things going on n nodes, has depth at least log n. You could have more, but it can't have less. Have you all done this claim before? It's kind of all these discrete math things that you might come across in undergrad class of discrete math. So let me make the claim properly here. This is a very important claim, by the way. This is about almost as important as the Bishnell principle. Have I told you the Bishnell principle? I have, right? Yeah, so this is almost as important as that. So, in fact, in one sense, this is the Bishnell principle, but we won't get into that. So, it's just binary digits. So, every binary tree on n nodes has depth at least how would you, but I'm not going to prove this right now, but how would you prove such a claim? Sorry?
Assume it's not true.
Assume it's not true, then what, how would you come up with common example? I mean, in other words, you're right, you would start with a contradiction, but why should it have depth at least long? Maybe that's a better way to ask it. Yes?
If we try to see in a way like what are the maximum number of nodes at each level?
Yes.
So at one it is like 2 raised to power 0, that is 1. At next it will be 2 raised to power 1, that is 2. So we can't have more.
You don't have enough levels
Yeah.
to get all the nodes you need unless you get beyond log n. Exactly, and you can work with calculation. So you'll say, suppose it's not true, suppose the depth is less than log n. We use that argument to say, okay, let's grow out one by one by one. The first level you have 1 node, next level you have 2, then you have 4. If you add them up, you get sum of 2 to the I from I equal to 0 to L minus 1, which is 2 to the L minus 1. And so if you set L equal to log n, that's the only way to get actually n nodes. So it's a simple calculation. Okay? And that's the idea. So in other words, you don't have enough different choices of different options for your nodes if you only have binary form. Okay. Let me rephrase this another way, right? Another way to say this is that a binary tree that has something like, I think it needs something like n over 2 leaves has going to have depth log n. It's the same version of the previous argument, right? If you think of a tree, you go out, you have 1 leaf at the beginning, you have 2 leaves, then you have 4 leaves, you have 8 leaves. You're not adding up now, but you're sort of putting out as many leaves as you can, right? Without increasing the level too much. If you have n leaves, you need that much depth to get there. Okay, it's the version of the same argument. So just adding up the number of nodes, you just look at the last level. In an exponential growth, the last level is all that matters. Now this version is going to be extremely important to us. Because here's the thing. If you think of your algorithm as a tree, and you think of depth as the running time of the algorithm, then this lemma here seems very important. Why? Because it's giving you a lower bound on a tree. It's saying that, oh, this class of trees has depth at least something, which is exactly what we wanted for our lower bound. But the proviso is that it must have at least these many leaves. And in the language of algorithms, if you think of a leaf as an outcome, a distinct outcome, every input sends you to some leaf. Different inputs might go to the same leaf. So if you are able to show that there are a large number of distinct outcomes based on different inputs, then different inputs will end up in different places no matter what the algorithm does, then you know from this lemma that you need at least a certain number of steps to get there. Correct. And then you're wrong. So that's the high level idea. So this is where decision trees start to be useful. They're a very primitive model of computation. And yet, because of this property of trees, we can reason about the depth of a tree and therefore the right type of algorithm very effectively. Okay? So let's take an example of a problem. So, so let's say I have the dictionary problem. Okay? So here's the problem. Okay, I give an array. It has a bunch of numbers in it. I give you a query, x. And the question is x in the array? If so, give me the index. If not, tell me no. Okay? I want to give a lower bound for this problem in the decision tree model. I don't know what my algorithm is doing, but I'm going to give it the lower. Okay? How many different answers would you need to produce from this decision tree? Let's say my leaves can be labeled now not just 0, 1, but with some specific answer. How many different answers do I need? Yes?
N plus 1.
Because there are n possible locations plus the not there. So there are n plus 1 possible locations. So any decision tree I come up with must have n plus 1 distinct leaves. And they must be distinct because I don't want to give an answer, well, maybe it's in position 3 or position 4. You want to give no. This is position 3, position 4, position 5. Each leaf is labeled appropriately. There may be many leaves with the label of 3 of them, depending on what the algorithm does. There's at least one. And it has to be different from the leaf for 4, different from the leaf for 5. So if we look at a decision tree, we don't know what our queries will look like. We have no idea what the tree looks like at all. That's the whole point. We don't know what the algorithms are. But we know that there's a box here that says 1. There's a box here that says 2. There's a box here that says n. And there's a box here that says not n. Right? And there are n plus 1 of these.
Can there be boxes which say the same answer?
Yes, but then there'll be more of them.
Yeah.
You could have many boxes saying 3. You could have many boxes saying 4, and that's perfectly fine. If you decide to come up with an algorithm that does it, that's up to you. But you must have at least one. Yes?
Is it compulsory to have all leaves at the same level in different trees?
No. In fact, the claim I made about the binary tree does not require you to have all the leaves in the same level. You can. This is true regardless. If you have these many leaves, you need that much depth. The proof is a little bit harder, but you can prove it by induction. You're right that the easy argument is for a balanced tree. And intuitively, that's kind of the worst case scenario because you're trying to pack in as much as you can. But it's not a proof. For a proof for any arbitrary tree with leaves in arbitrary levels, then you can actually show it by induction that, in fact, if you have n leaves, you need at least longer levels. And in some sense, if you stop a few leaves early, then you need to pay for a lot more depth later on. That's the intuition. You can prove it. Good question. So now I have n leaves. I invoke my starred claim. Every binary tree with n leaves has depth at least log n. Done. Any decision tree for solving the dictionary problem must spend at least log n decisions. That's it. Very simple. All I had to show was that there must be at least these many leaves. Can you solve the dictionary problem in log n time? So I give you a lower bound, it takes at least log n time. Can you actually do this in log n time?
Yes.
Yes?
It's sorted, then you use this
Sorry?
binary search.
If it's?
If it's sorted, then you can do binary search.
You can. And I don't know what it needs to be sorted because I haven't said anything yet about whether the data is sorted or not. I'm making assumptions, so you could. You can do it better actually. You can do it in constant time. Can you do dictionary search in constant time here? How?
Hash table.
Build a hash table. So I can get expected or even worst case constant time to figure out an element. But this is saying it takes me log n time.
No, but hash table is a probability, right? It's an
I can get yes, but I can get for any particular table, I can get a hash table that will be constant access time. Yeah. So yes.
Well, isn't the hashing function itself not necessarily constant?
That you're on the right track. Let me rephrase what you just said. The hashing process itself does not come into the category of a decision. I'm making sort of I'm doing things with the data that you know are not sort of generic. Well, actually, that's not quite right. Let me say this correctly. Okay, hold on. The thing is that a hashing result outputs many possible answers. So if you think of what you're doing with hashing, you're taking a number and you're producing this other number from it. There aren't two possible outcomes from that. There are many possible outcomes from doing that hashing. You're outputting many bits in some sense. A query gives you a bit, just 0 or 1. And this whole 0, the whole 0, 1 thing is very important if I want to get log n, because my base is 2. If I have a query that can output many possible answers, because I have many possible hash values, and based on the hash value I do something else, then my fan out of my tree is much higher. In fact, if my fan out is something like n, then it's log base n of n, which is 1, which corresponds to hash. So again, we are doing a very limited model, right? Decision trees are very simple model. However, there are simple decision trees that we do come across in practice. Suppose my decision was always a comparison. I was comparing two numbers and saying which one is bigger. Then my answer is either 0 or 1. And you can think of algorithms you've designed that use exactly that property. Binary search, for example, uses that property. And binary search takes log n time. So this model is, while being unrealistic in general, actually captures an actual algorithm that you use, which is binary search. But what it's also saying is that if you are only willing to compare two numbers and output a number saying something about them, a 0, 1 answer, you will never be able to do better than log n. If you want to go beyond log n, you have to be more clever. You have to do more things with the numbers than just compare them. And that's the whole point of Lord 1 also. They tell you which avenues for improvement are blocked off and where you need to go. Okay, next problem. So we've looked at dictionary search. Let's look at sorting. And since we want to do the ideal like some kind of yes/no answer, we're going to rephrase the sorting problem. So sorting problem in this context is going to be something like this. Given x1 through xn, find a permutation pi such that x pi 1 is less than x pi 2, assume they're all distinct, less than x pi n. So in other words, find the rearrangement of the inputs so that now they're all in sorted order. Okay? Alright. So again, how many distinct outcomes could you have? How many permutations do you have on n elements? N factorial. In other words, your output could be any possible permutation. And if you think that's unlikely, think of it this way. Suppose I took an input that is sorted and applied a permutation to it. what is the output going to be then? The output will have to be the inverse of that permutation, right? And I can do this with any permutation. So I can think of any possible input. So I can have any possible permutation here. So if I have a decision tree where the number of leaves is the number of permutations, because each one of them is a possible answer for my input, then I have n factorial leaves. And so the depth is greater than or equal to log of number of permutations, which is equal to log of n factorial, which is roughly n log n. You can be more precise, and that's in the notes. Yes?
Does a decision of choosing the machine change the outputs that we can get?
Yes, and it also changes the notion of cost, it changes everything. So every time you prove something in a particular machine model, if you change the machine model, you're going to throw everything you've done to start from scratch. Okay, sometimes maybe you can borrow something, but for the most part, you have to start again. Every machine model is different. The decision tree model is different.
What is your decision here? Because you said yes.
I don't know. It's just anything that allows me to give a yes/no answer.
But I can do based on decision model, then your lower bound is n log n.
Right.
Not on any other model. On the other model.
Only decision model. Whenever someone gives you a lower bound, your first question to them has to be, what is your model? If they can't answer the question, they're not giving you a lower bound. They give you some hand-wavy nonsense. A lower bound and a model go hand in hand. One is not meaningful without the other. Very important. This is, like I said, when we think of upper bounds, we think implicitly just in terms of the random model, just regular, a random access machine and whatever. But for lower bounds, you have to be a lot more precise. Okay. There are models of computation, for example, where P is equal to NP. There are models of computation where P is not equal to NP. It's good to know which model we're talking about. And if you don't know P and NP, you'll hear about that very soon. Okay, so we proved n log n, that's fine. But again, is this a realistic decision tree? Is it a realistic model of computation? I mean, is there any algorithm that can give you n log n, the decision tree model? Maybe the model is so hard that any actual algorithm would take, n cube time. Do you have an actual algorithm that will take n log n time in the decision tree model? Can you think of one? Merge sort. Or quick sort with medium pivot, I guess, but let's say merge sort. Think of a sort of a classical sorting algorithm. What is the operation it does? It says, let me compare two elements and do some work based on that. Let me compare two more elements and do some work based on that. I'm making binary decisions at every step. In fact, I'm making a very, very simple kind of decision. I'm just saying, compare two elements and tell me what's bigger. It's even simpler than decision tree. And I can get n log n. In particular, I can do n log n comparisons in this model. So, merge sort takes n log n time in the comparison model. And then if you look at the decision tree model here, this is the comparison model here. It's a very special case of a decision tree when you're only doing comparisons. You could be doing something more complicated. You could compute some function of a bunch of numbers and like a polynomial and look at the sign of the polynomial. You could do all kinds of things, but I'm just doing comparisons here. So if we're saying that there's a lower bound of n log n in the decision tree model, and I can compute an algorithm, I can give you an algorithm that runs in n log n time in the comparison model, and I'm right, then I can say this algorithm is optimal. It can't do any better in this model because I've matched the lower bound. So when I say merge sort is optimal, what I mean is merge sort is optimal in the decision tree model or the comparison model. That's what optimal means. Can you sort it better than log n time? Yes. How do you sort it better than log n time?
You have a bunch of zeros, and you do something like sort.
Radix sort. Is radix sort not a decision tree model? What kind of operations are you doing on is radix sort, let me rephrase, is radix sort not a comparison model?
It's a comparison, not of two objects at one time.
About it.
Because if you know everything in one bin, then you're essentially comparing everything, all the items of one bin to another bin.
Exactly, and you're looking at bits. You're looking at bits of items. You're doing much more with the input than like just comparing them blindly and saying which one is bigger. So you're violating the model, so it's not surprising you can do that. So again, the lower bound is only as good as the model. No better, no worse.
Excuse me, what do you mean by convection model?
That the operation I'm performing at every node of the tree is a comparison of two elements. And I decide which one is bigger, and based on that, I take a path. So the node operation for sorting looks like this.
So what difference between convection model and DTM?
Sorry?
What's the difference between CM and DTM?
Good question. What is the difference? Well, in a general decision tree model, here's my question. Here could be my question. This could be a node in the decision tree. I could be doing all kinds of stuff. All I know is that there are two outcomes. There's a yes and there's a no. Whereas in the comparison tree model, I'm just saying it's what is called a linear decision tree model. A very special case of a linear model. Okay? Yes?
So what about insertion sort on a sort of list?
What do you mean?
You're using the comparison model, but the lower bound is linear.
Lower bound is n log n. Because log of n factorial.
Not for insertion sort, though, right? Because it's best is
What?
linear when it's
Insertion sort.
for a sort of.
Oh, what is the worst case sorting time of insertion sort?
That's sort.
So I remember I'm giving a lower bound and the worst case time. I'm not giving a lower bound
Right.
the best case time, but it's a good point. Yeah. You first take the max over the algorithm, the inputs to the algorithm, then take a min after that. If I flip the if I didn't do the max first, then you're right. Insertion sort has a timer n on a perfectly sorted input. But I'm looking at the worst case input for insertion sort first, and then looking at the best case, worst case time. Make sense? Yeah. Okay. Good. So this is the most sort of basic tool for proving lower bounds. You basically say something like, I'm trying to think of my space of possible answers. Okay? I have an input, and there's a space of possible answers, and I have to go find one. The only operation I have is this machete that allows me to sort of cut through the jungle that I'm going through, this jungle of it. So I cut through the jungle, I make one move. I cut again, I make another move. And I can't see any further than that. And so if the inputs are all scattered and they're far enough away, there's someone who's far enough away, it's going to take me a lot of cuts to get there. And that is the sort of the much more picturesque sense of what a decision tree model is about. There are lots of inputs, therefore some of them are far away because they're all reasonably far from each other. And I have only a simple machete. If you now give me a bazooka or give me like a laser beam, like just cut through the entire window, then of course I can see more. And then it would take me less time. But then that changes the model altogether. So it all depends on the model. Any questions? I went over really long, so let's just take a 2-minute break.
That was the place I went. Like, I don't know what kind of
Oh, that's
I was like, it's like,
That's where our because
I tried to put out I was going to bring you back to you guys, but it goes back. Like if I bought it like right like a month, it would be starting to go back.
Okay, let's continue. New problem. So we've seen lower bounds for, let's see, we've seen lower bounds for the dictionary problem. Something like log n. We've seen for sorting, which is n log n. What about for a simpler problem in sorting, something like find the max? It's an interesting problem here. If we had to use our decision tree module that we've developed so far, so we might say, okay, we have a decision tree, we need to know the number of leaves. So specifically the max would be, given an array, tell me the index of the item that is the largest in the array. That's one way of asking the question. Okay? Not the item, the index of the item. Because then I can just look it up. How many outcomes are there? Just, there are n outcomes, because any one of the items will be the largest. Right? So in our decision tree world, what is the lower bound for maximum? If there are n items, the decision tree lower bound would be log n. Pardon me? Let's assume they're distinct for now. Because if they're not distinct, it gets even easier in some ways. Because then, when I have to answer, it's item number 5 or item number 6, I can give either of them. I don't even need that many values. Let's assume I make it as hard as possible. They're all distinct. And so, we need log n. Can you actually solve the max in log n time if you don't sort the array? If I have an arbitrary array, can I do max in log n time? Seems hard. Seems like I'd have to look at every item. How would I know if I miss an item? How would I know if it's a max or not? And in fact, it's true that if you're only willing to make comparisons between items, you're not allowed to do anything more clever. Right? You just can compare two items and see which is bigger. It actually takes you much more than log n time. So we talked about the decision tree model and the comparison model. We said, oh, in the decision tree model, the lower bound is n log n, and in fact, you can match to the comparison-based algorithm. This is a case where the decision tree lower bound is in fact log n, but any algorithm you might think of will take much longer. So for example, here's what I could do. Suppose I want to find the max in log n time in the decision tree model. That means only using the model, not counting anything else. So here's my first question. Is the lowest bit of the index of the maximum item 0 or 1? So tell me, okay, 0. Is the second lowest bit of the index of the maximum item 0 or 1? Tell me it's a 1. How many queries do I need to get the answer? I need log n queries. So this is actually correct. But can I implement this algorithm? No, I can't. This doesn't make any sense. As an algorithm, it makes no sense. Because it's assuming all kinds of stuff that the model doesn't talk about at all. Like how on earth am I supposed to answer the question of is the lowest bit of the index of the maximum element 0 or 1? But the decision tree model doesn't prevent me from doing that. So what I'm trying to say is that when we think of these models and lower bounds, they're very stylized. They're not meant necessarily to give you what a real algorithm would look like. They're meant to help you think about which operations are really important to solve the problem. When we say that we want a decision tree lower bound, we're saying that somehow asking questions is the way to the answer. That's the key to understanding the problem. But for the purpose of doing the max, doesn't appear to be true. Because asking questions about the answer gets us there, but we can't actually implement that. I don't know how to implement it. So let's weaken the model a bit. Let's go to the comparison model where you have to ask very specific kinds of questions. You're not allowed to ask about the bits of the index or the max value. You can only compare two elements. But even then, we only have n outcomes. It will say it's log n complexity in the comparison tree model, the same argument as before. So that's not useful either. What you need in this case is something a bit more. You need what is called an adversary argument. And this is at the heart of, in some sense, everything we do in algorithms, even for upper bounds. Remember for upper bounds, I told you to imagine some adversary who's trying to give you bad inputs and try to use that to test if your algorithm is correct. Here we use this formally to prove lower bounds. And the premise is the following. When we reason about, oh, the number of leaves in this tree is n, and each branch is binary, therefore we need log n depth. We are making what is called an information theoretic argument. We are saying that there is a certain amount of information in the system, because there are n outcomes. So you need at least log n bits to describe each outcome. You can think of the bits as being constructed as you go along the path. And so the length of the path is the number of bits you need to describe the outcome, which is going to be log n. And that's purely information theoretic, because it's merely saying, well, I have a bunch of data and I have to describe each one of them. There is nothing computational about this at all. In fact, it is shocking that you can get so many lower bounds just by this kind of information theory argument. And so a lot of what we do in computer science is also learn about information theory, because it helps us here. But somehow that's not enough in this particular case. Because it's saying that there are n possible outcomes for the max, and so I need log n bits, but I don't know of a way to actually do that. Right? The information theory is not the same as the algorithm itself. And what this is saying is that somehow it's not enough to say that, I have so many inputs. The input is somehow reacting to my questions. That the input is being constructed in a way to subvert my algorithm. And that's your adversary. So the input doesn't come ahead of time. It's kind of dynamically changing as you ask questions to make your life even more difficult. So we're going to play a game here. We're going to play a game where the algorithm is going to ask, okay, is item I more than item j? And the adversary is going to answer the question. The adversary is not allowed to lie. But the adversary can kind of answer questions any way they want as long as their answers are eventually consistent. Right? I can't say, for example, I'm not allowed to say that if the algorithm asks me, is x1 less than x2? And I say yes, and it says is x2 less than x3? And I say yes, if I'm the adversary. I cannot now say is x3 less than x1? I can't say yes. This is not allowed. Because this would be inconsistent. I have to give consistent answers. But I can give the answers as the algorithm asks. So the game is the following. The algorithm is going to ask me questions. I'm going to give answers. And I'm going to give answers in such a way that the algorithm has to keep asking. That they cannot stop asking because they would get the wrong answer. Because if they stopped asking at any point, I could then give actual values to the input that would declare their answer to be wrong. So let's maybe try this game. Right? So let's say there are 3 numbers. Okay? Or let's say there are 4 numbers in the list. Okay, so I have x1. So I have some unknown input. x1, x2, x3, x4. Let's say you're the algorithm. And you want to find the max in in 2 comparisons or less. That's the reason I'm choosing that. I haven't constructed the input, but the input is kind of not there yet. Tell me what your first question is going to be. Allow 2 questions or less. I want to find the max. What might you do? So you're allowed to ask me about any 2 elements, and I'll tell you which of them is bigger. So ask a question.
Can you sum elements? Can you say like is x1?
No, I'm only allowed comparisons. That's the point. That's the weakness of the algorithm. Very good, yeah.
I'll ask you if x1 is greater than x3.
Okay, so wait. So your first question, 1, is x1 greater than x3? I say yes.
then I'll ask you is x2 greater than x4?
I say yes. Tell me what the max element is. Huh?
I need one.
No. Tell me what the max element is. You have to tell me. I insist. Declare which element is the max. No, there's a reason I'm saying this. Declare. Your algorithm is claimed. Your algorithm is saying I can do this 2 comparisons or less, and I'm the adversary. Okay, fine. Now tell me the max. Tell me the max now, because you claim you can do it. Don't think about, oh my god, I can't do it. You're the algorithm. You're confident. You know you can do it.
It's x1 with 50% accuracy.
No. What 50% accurate? Don't hedge. Is it x1 or not?
It's a random variable.
No. It's a deterministic algorithm. Declare your answer. Don't be a politician.
X1.
X1 is the answer. Okay. So the algorithm says X1 is the answer. I am now, as the adversary, going to produce an input. Okay? That will make this algorithm wrong. So I have to make X1 more than X3. I have to make X2 more than X4. I have already said yes. I can't change that. So this is easy, right? I'm going to say that my answer is going to be 5, 10, 2, 1. This is no surprise to you, right? The algorithm is obviously wrong here. But here's the point. The mechanics of this process are very important. The algorithm is going to ask me questions. I haven't yet told you how I made these answers, but I'm going to make answers in a certain way. Okay? And then the algorithm is going to stop. And then I'm going to construct the input, the real input. Remember, the algorithm didn't know what the input was. All I needed were comparisons. So as the adversary, I'm allowed to delay actually constructing the input. So I do this at the end, and now the algorithm turns out to be wrong. How do you make a formal proof on this? Is the question. I want to show now, and here's what I'm going to tell you. I want to prove to you that any comparison-based algorithm for computing the max requires n-1 comparisons. No less, which is much bigger than log n. How am I going to play this game to make that happen? Yes, okay, so I should say this point. That is always correct. I mean, most of the time you'll be doing a proof by contradiction. What I'm asking for is how. Yes?
Sure that we can't make a input that contradicts our algorithm if we're allowed to ask at least n questions.
No, but I want to prove you must take at least n-1.
Oh.
I didn't say you can't take at least 2n.
Well, then just make an output that says
What we want to show is that if the algorithm stops asking questions before n-1 and then produces an answer, I am still able to produce an input on which that algorithm is now wrong. If the algorithm says x1 is a max, I will produce an input on which x1 is not the max. Yes?
So what if we start with log n comparisons, like log n questions, then we are able to produce a sequence which reject our log n sequence answer. Then we do log n plus 1 and go till n-1, because each time we can prove that we have an input which reject your answer.
Right, but the algorithm might not be required to produce the correct answer all the way to n-2. It might do, I don't know, well, it has to get n-2 and then produce an answer. So in other words, the algorithm may not say what the answer is, still n-2 comparisons. And I don't know what the algorithm is doing. All I know is the questions it's giving me. So I'm the adversary. So here's the game I'm going to play. Every time, so here's my game. So when the algorithm asks the question, is xi more than xj? Okay? Here's what I'm going to do. So first of all, the adversary initially pretends that xi is in fact I. So first of all, so hold on, let me just. So the adversary assumes xi is equal to I. So when the algorithm asks, is x1 less than x2, it'll say yes, because I'm going to treat x1 as 1 and x2 as 2, just for now. Okay? And then, when the algorithm asks is xi more than xj, right? The adversary answers the question, right? And mark xj. So the adversary is keeping track of all the inputs and is going to mark xj. Why is the adversary going to mark xj? If xj is smaller?
It's not the answer.
Because now xj can never be the max. I've just said that xi is more than xj. So marks xj if yes and xi otherwise. So the adversary is marking the element that it knows can never be the max. Okay? Now, suppose the algorithm asks about. Okay, so now, the algorithm is going to ask a question. I don't know what it's asking. In the beginning, all the elements are unmarked. The adversary uses this rule to figure out how to answer the question and what to mark. At some point, the algorithm is going to ask about a marked element, right? So let's see. So the adversary the algorithm might ask about what about xi more than xj, where xj is marked. Again, the adversary just uses the current known values of these things to answer the question. The claim is that one new element is marked. I will never mark two elements. If I'm comparing two elements, I will never mark them both. Yes? Because at every step, either the element's already marked, in which case I haven't done anything, or I'm going to mark one new element. So each one new element. So after n minus 2 questions, right? Remember I said we pretend xi is equal to I. After n minus 2 questions, there are two candidates for the maximum value, right? One candidate and some xk are unmarked. Right? Yes?
I have a doubt. So what if we first compare 5 and 3, so we mark 3 and
You mark the element whose, you mark the 3 is the index or the value?
Maybe, what
Okay, so you mark x3, yeah, okay.
We mark 3 and then we compare 6 and 2, we mark 3.
Yes.
Then what if we compare 3 and 2, both are marked, or we don't allow?
Well, then you're not adding a new mark. You're asking a question, but you're not increasing the number of marks. I still have only 2 marks, right?
So we don't take those things where both are marked, is it like that? We are not-
You can. The algorithm can do whatever it wants. What I'm saying is that the adversary doesn't need to keep, it can remark 2x2, whichever one you had, as not the max, but I already knew that. So it's not adding any new marks to the set, is what I'm trying to say. Right? So at the end, there are 2 elements that are unmarked after n minus 2 questions. Okay? Now the adversary tells the algorithm, okay, what's your answer? You told me you'll give me the answer in n minus 2 comparisons. So either the algorithm gives something that's not one of these 2, which is clearly wrong, because I marked it, which means there's some element that's more than that. So the algorithm is wrong. Or the algorithm gives xn, or it gives xk. It has to give one of these 2 choices, right? Whichever one it gives, I now construct an input where the other one was the max. Like in your x1, x2 example before, x1 and x2 were the 2 unmarked elements. You chose x1, I made x2 the max. And I can do this consistently because neither of these 2 elements are marked, so there's no constraint on what they need to be. I can make them whatever I want. Because I have not asked a question where one of them is less than something else. Yes?
So I just have a question about the claim. So if I had like an xi and an xj and then an xk,
Yeah.
but I knew xj was greater than xk.
Because you asked.
Well, I mean, or I just knew. I guess I'm asking how you come to this claim. I mean, we have to assume it's unsorted.
Right, so the data initially, the algorithm knows nothing about the data.
Okay.
Every time the algorithm asks a question,
Right.
the adversary marks at most one of the two elements.
Right.
That's all.
Sure.
That's it. That's all the claim is saying.
Oh, okay. Right.
It's a property of what the adversary is doing. The algorithm has no clue what it is.
Right.
It's my internal bookkeeping that I've kept. See, as the adversary, I'm trying to do this internal bookkeeping to fool the algorithm. This is a claim about my internal bookkeeping, and this is then letting me do something at the end. I know that at the end I have two elements that are unmarked because of my bookkeeping, and so when the algorithm says, "Okay, my answer is XN, give me the input," I'm going to get it pretty simple. So the algorithm knows nothing about any of this stuff, and I don't know what the algorithm is asking. That's the hard part of this reasoning. I don't know what the algorithm is doing. All I'm getting are the questions it's asking, and I have to build some bookkeeping based on that. And so this kind of adversary argument comes up a lot in algorithm design, where you imagine some adversary playing a game against you, where they're trying to hold back and force you to do more work and more work and more work and more work. And that's how you reason works. So it goes beyond the simple decision tree Lower bound. It's a more dynamic version of it, because it adapts to what your questions are asking. The tree itself changes in some sense. You force the tree to change as you learn. And that gives you the aim Lower bound. So if there are two questions, you fail, just to complete the argument. If after it two questions, the algorithm declares the answer, you choose the other one to be the one max, and you construct it, okay, this is my input, you got it wrong. So the algorithm can never win unless it asks at least set transformations. Yes?
You use XN, but if it's a formal group, it's a formal group, I can't use XN.
No, it is, because what did I say? I said, let the adversary assumes in the beginning that xi is equal to I. So xn would in fact be the max.
Then you might,
the algorithm doesn't know that.
The algorithm would have asked, is XN greater than X3 or something?
Sure, then I mark xn.
And
Then I would say yes. In fact, xn is more than x3, I mark x3.
oh, and you
xn will never get marked by design. The problem is there's one other element that will get marked as well. That's the problem. xn will always be the right answer. The problem is distinguishing the two. So the game with every kind of lower bound you will see, not just one more minute, is that the adversary will play some game, so at the end of the process, if the algorithm has not spent enough resources, there will be more than one possible outcome. And the algorithm will not know which is which. And then you will supply the wrong one after giving the answer. So in some sense, it is information theoretic, in the sense that the algorithm does not have enough bits if it asks your questions. But you're constructing this on the fly. So it's more mutual information than entropy. All right. See you on Thursday.